Hello, my name is Hunter.
Hello, my name is Pierre-Alain.
Hi, my name is Manfredo Marroquin.
And this is our presentation on the defects and diffusions of our materials. So for question one, it asks us to find the number of vacancies in 1 cubic centimeter of both of our metals. So to find that for iron, we're going to multiply the number of sites by a pre-exponential factor that dictates the sort of number or percentage of vacancies that you expect to see among the sites. So firstly, to calculate the number of sites, we're going to calculate the number of atoms in that cubic centimeter. So to do that, we divide the total mass by the mass of an individual atom, which is the volume of the total cube times the density of the cube, and the molar mass of an iron atom divided by the number of atoms in a mole. So you can see that here is 1 cubic centimeter. The density of iron is 7.87 grams per centimeter cubed. The molar mass of iron is going to be 55.845 grams per mole, and then Avogadro's number is still there. When you calculate that out, you get a total of 8.487 times 10 to the 22 sites. So then for our pre-exponential factor, this is a value that was looked up or experimentally determined. Is going to be 0.55 at 211 Kelvin. So we plug these values into our equation. We can solve for that now, and we get 7.365 times 10 to the negative 14. So now with these values calculated, we can go on and plug them back into our equation for the number of sites and our pre-exponential factor. And once we do that, we get the number of defects is going to be 6.25 times 10 to the 9 vacancies. So that's going to be the number of vacancies per cubic centimeter of our material. So for nickel, we just take the sort of same approach. We're going to calculate the number of sites, multiply it by our pre-exponential factor. Once again, same approach, 1 cubic centimeter. We have a new density now of 8.9 grams per cubic centimeter, a new molar mass of 58.69 grams per mole, same Avogadro's number. When we calculate that out, it's going to be 9.132 times 10 to the 22 sites now. And our pre-exponential factor, once again experimentally determined, was given as 0.98 at room temperature, which is 293 Kelvin. When we calculate that all out, we're going to get the pre-exponential factor is 1.408 times 10 to the negative 17. So we're going to plug those back into our equation. So we have our new values, and we can solve for the number of defects now, which is going to be 1.286 times 10 to the 6th vacancies. Once again, that is for the number of vacancies within that cubic centimeter.
All right, so we're going to be talking about Frenkel defects and Schottky defects. For this slide, we're going to be talking about like the number of Frenkel defects. This is the formula we're going to use, and it's the number of vacancies or defects in the volume that we're using. In this case, 1 centimeter cube. QFR, that's the Frenkel defect activation energy unit, which in our case will be 2.51 eV. K is equal to the Boltzmann constant, which is 8.617 times 10 to the negative 5, and T is our temperature. We chose 293 room temperature. Over here, this is the formula that we use to find the number of vacancies per centimeter cubed, n being the number of n is the Avogadro number. That's rho for density and area of indium phosphide. So when we throw all in, we get 1.987 times 10 to the 22 vacancies per centimeter cubed. Moving over here, we throw it in here, and it's being multiplied by the exponent of the variables over here, which gives us a final Frenkel defect number of 5.136 defects per centimeter cubed. Now we're going to do the same thing for the Schottky defects. Same thing, n would be the same. So over here, same number, that's not going to change. Really what's only changing is the activation energy for Schottky defects, in this case being 0.89, which is expected. Schottky defects Activation energy is typically lower than a Frenkel defect. Same thing, Boltzmann constant T is equal to 293 Kelvin. So when we plug it all in, we end up with 2.402 times 10 to the 22 Schottky defects per centimeter cubed, which tells us that there's a lot of Schottky defects and not many Frenkel defects in our semiconductor, in this case being indium phosphide.
So in the third question, we asked to find the diffusion length of carbon in iron at 300 Kelvin in 1 minute. So to do that, we're gonna use this formula, L equals square root of D times T, T here being the time in second, and D is the diffusion coefficient. And we also know that D is equal D naught, the diffusion coefficient of carbon in iron, times the exponent of minus Qu, which is the activation energy, divided by RT, this T being the temperature in Kelvin. So we're gonna try to find D first. So to find D, we're gonna plug the numbers. So D naught in our case, the diffusion coefficient of carbon in iron is 6.2 times 10 to the minus 7. So we plug that in, and the activation energy is 80 here. So we just plug all the numbers, and that's what we got for T, 7.177 times 10 to the minus 21 meters squared per second. So once we have all the numbers, we plug that number here in the original formula, times 60, 60 being 60 seconds because we asked to find it in 1 minute, and we obtain the result being 6.56 times 10 to the minus 10 meter. And now we're gonna find the diffusion length of carbon in iron, this time at 60 Kelvin in 1 minute. So it's gonna be the same method. We're gonna use the same formula, but what's gonna be the difference is the temperature. Instead of plugging in 300 here, we're gonna plug 60. This is what we did here. D naught is still the same, the diffusion coefficient of carbon in iron, and this time for D we obtain 6.67 times 10 to the minus 14 meter squared per second, and the length, the diffusion length is gonna be 2 times 10 to the minus 6 meter. In the fourth question, we are asked to find the diffusion length for silicon in indium at 300 Kelvin in 1 minute, then 600 Kelvin in 1 minute. So the formula we're gonna use is the one we used previously, L equals square root of D times T, T here being the time in second, and we also know that D is equal to D naught, the diffusion coefficient, times the exponent of minus Qu, the activation energy, divided by RT, R here being the time, no, the temperature, excuse me. So we're gonna try to find D first and then plug it in the original formula. So here the D naught, the diffusion coefficient of silicon in indium, is 1.8 times 10 to the minus 11 meters squared per second. So that's the number we plug in, and the activation energy is 285.6 times 10 to the 3 joule per mole. So we plug the number here, and we plug all the numbers, the constant and the temperature, and we end up with 3.18 times 10 to the minus 61 meters squared per second. So that number that we found here, we're gonna plug it in the original formula, and we multiply it by 60 seconds because we have to find it in 1 minute. So the final result is 1.38 times 10 to the minus 26 meter. So for the diffusion length of silicon in indium at 600 Kelvin in 1 minute is gonna be the same method. We're gonna use the same formula, but what's gonna change is the temperature here. Instead of plugging 300 like we did here, we're gonna plug 600 because it's 600 Kelvin. The diffusion coefficient is still the same, and the activation energy is still the same. This time we end up with 2.39 times 10 to the minus 36 meters squared per second, and we plug it in the original formula. So we plug that number here, and we will still multiply it by 60 seconds, and we end up with 3.788 times 10 to the minus 14 meter. So thanks to all of you for watching our presentation about the defects of different materials. It was Pierre-Alain Gbalou,
Hunter Sanford.
And Manfredo Marroquin.